NENOMATICA, where mathematics meets YouTube excellence. In this video, we will prove a fundamental property of the floor function. The theorem states, for any integer n, the floor of x plus n equals the floor of x plus n. Let us begin the proof, step by step. Step 1. Set the value of the floor function. We assume the floor of x equals n, where n is an integer. Step 2. By the definition of the floor function, n is less than or equal to x, and x is less than n plus 1. Step 3. Add n to all parts of the inequality. This preserves the inequality direction. Step 4. Simplify the expressions. N plus n is 2n, and n plus 1 plus n is 2n plus 1. Step 5. Apply the reverse definition of the floor function. If a number lies between k and k plus 1, its floor equals k. Step 6. Rewrite 2n as n plus n using substitution. Step 7. Replace the first n with the floor of x using our initial assumption. Therefore, the property is proven. The floor of x plus n equals the floor of x plus n. Quick check. Let x be 3.7 and n be 5. Then floor of 3.7 plus 5 equals 8. And floor of 3.7 plus 5 equals 8 as well. In this lesson, we will evaluate a floor bracket expression step by step, focusing on clear, visual reasoning. Here is our problem statement. We want to compute the floor of the fraction, open bracket, 2x squared plus 3, over x squared plus 3, close bracket. Step 1. Decompose the numerator. We rewrite 2x squared as x squared plus x squared to match the structure of the denominator. Step 2. Split the fraction using the sum over a common denominator. Recall the identity, open parenthesis a plus b close parenthesis, over identity, open parenthesis a plus b close parenthesis, over c equals I over c plus b over c. Step 3. Simplify the first fraction. Any non-zero quantity divided by itself is 1. So, x squared plus 3 over itself becomes 1 inside the floor bracket. Step 4. Use a key floor property. The floor of an integer, n plus a term equals n plus the floor of the term whenever n is an integer. Since 1 is an integer, we can move it outside the floor. Step 5. Range analysis. For any real x, x squared is non-negative, and x squared is strictly less than x squared plus 3. Therefore, the fraction x squared over x squared plus 3 is at least 0 and strictly less than 1. The floor of any number in the interval from 0 inclusive to 1 exclusive is 0. Let's visualize that on a number line. Hence, the entire expression equals 1 plus 0, which is 1 plus 0, which is 1. Final answer, 1. In this lesson, we will compute the floor of the expression, the floor of open parenthesis 2 plus square root of 3 close parenthesis raised to the 4th power. We will follow a clean 5-step plan that uses conjugates and bounding. Example, problem. Compute the floor of open parenthesis 2 plus square root of 3 close parenthesis to the 4th. Step 1. Define the conjugate pair. Let x1 equal 2 plus square root of 3, and x2 equal 2 minus square root of 3. Their sum is 4, and their product is 1. Therefore, x1 and x2 are the roots of the quadratic x squared minus 4x plus 1 equals 0. Step 2. Compute the symmetric sum a equals x1 to the 4th plus x2 to the 4th. Use the identity x1 to the 4th plus x2 to the 4th equals the square of x1 squared plus x2 squared, minus 2 times x1 squared x2 squared. Now, x1 squared plus x2 squared equals the square of x1 plus x2 minus 2 times x1 x2. Substitute the values 4 and 1. We get open bracket 16 minus 2, close bracket squared, minus 2, which is 194. Step 3. Connect the target to A. Since x1 is 2 plus square root of 3, and x2 is its conjugate, we have x1 to the 4th plus x2 to the 4th equals 194. Therefore, x1 to the 4th equals 194 minus x2 to the 4th. Taking the floor of x1 to the 4th equals the floor of 194 plus the negative of x2 to the 4th. Because 194 is an integer, The floor distributes as 194 plus the floor of negative x2 to the fourth. Step 4. Bound the conjugate power. Since square root of 3 is approximately 1.732, we have 2 minus square root of 3 is strictly between 0 and 1. Raising to the fourth power keeps it strictly between 0 and 1. Multiplying by negative 1 flips the inequality, so negative 1 is less than negative of that power, which is less than 0. Therefore, the floor of negative of that power is negative 1. Step 5. Finish it off. Substitute the inner floor result back into the expression. The floor of open parenthesis 2 plus square root of 3 close parenthesis to the fourth equals 194 plus negative 1, which is 193. As a quick check, 2 minus square root of 3 to the fourth is about 0.005. So the value is about 193.995, and its floor is 193. To summarize, we paired the expression with its conjugate, computed a symmetric power sum, used an integer floor shift, and bounded a small positive term to conclude the floor equals 193. In this lesson, we will prove a beautiful identity about the floor function. We want to show that for every natural number n, the quantity floor of n over 2 plus floor of n plus 1 over 2 equals n. Here, square brackets denote the floor function, meaning the greatest integer less than or equal to the number inside. To build intuition, let's look at a quick number line example. The floor of 3.7 is 3, because 3 is the greatest integer less than or equal to 3.7. Now let's test the identity for a few small values. We will compute floor of n over 2, floor of n plus 1 over 2, and their sum for n from 0 to 7. Notice how the sum always equals n. Let's now prove it formally using two cases, even and odd. Case 1. Assume n equals 2m, an even number. Substitute n equals 2m into the left-hand side. Then simplify term by term, using that m is an integer and the floor of a half is 0. Case 2. Assume n equals 2m plus 1, an odd number. Substitute and simplify step by step. Example. We will solve and explain step by step a neat identity using the floor function. Here is the problem statement displayed in bold orange. If the floor of 2 times open parenthesis x squared plus 9 close parenthesis equals the floor of 12x, compute the floor of open parenthesis x plus 3 close parenthesis squared. Step 1. Define an auxiliary integer n so that both floors are equal to n. That is, the floor of 2 times open parenthesis x squared plus 9 close parenthesis equals n, and the floor of 12x equals n. Step 2. Use the definition of the floor function. If the floor of equals n, then n is less than or equal to a, and is less than n plus 1. Apply this to both expressions. Step 3. Divide all parts of each inequality by 2. This preserves the inequality direction because 2 is positive. We get n over 2 less than or equal to x squared plus 9, less than n plus 1 over 2, and n over 2 less than or equal to 6x less than n plus 1 over 2. Step 4. Add the inequalities term by term. Left sides add to n. The middle becomes x squared plus 6x plus 9. The right sides add to n plus 1. So we obtain n less than or equal to x squared plus 6x plus 9 is less than n plus 1. Step 5. Recognize a perfect square. X squared plus 6x plus 9 equals open parenthesis x plus 3 close parenthesis squared. Therefore, n less than or equal to open parenthesis x plus 3 close parenthesis squared is less than n plus 1. Final step. By the definition of the floor function, if n is less than or equal to a quantity and that quantity is less than n plus 1, then its floor is n. Hence the floor of open parenthesis x plus 3 close parenthesis squared equals n. Since we defined n to be the floor of 12x, the answer is the floor of open parenthesis x plus 3 close parenthesis squared equals the floor of 12x. As a visual intuition, imagine any real x that makes both initial floors equal to the same integer, n. Our algebra squeezed open parenthesis x plus 3 close parenthesis squared between n and n plus 1, forcing its floor to be n as well. In this lesson, we will solve a neat floor function identity. The goal is to find the value of the expression floor of n over k minus floor of n minus 1 over k, given that n is not divisible by k, and n and k are natural numbers. We'll prove the result algebraically and also build intuitive number line visuals. Here is our expression and the given condition. Step 1. By the division algorithm. Since n is not divisible by k, we can write n equals mk plus r, where m is the quotient and r is the remainder, with r strictly between 0 and k. That is, r is greater than 0 and less than k. Step 2. Substitute n equals mk plus r into the difference of floors. Step 3. Split the fractions. This becomes floor of m plus r over k minus floor of m plus r minus 1 over k. Step 4. Use the key property of the floor function. For any integer m and any real number x, floor of m plus x equals m plus floor of x, applying that here, the m values cancel. Step 5. Since r is between 0 and k, the fraction r over k is strictly between 0 and 1, so its floor is 0. Also, r minus 1 is at least 0 and less than k minus 1, so the fraction r minus 1 over k is between 0 inclusive and less than 1, and its floor is also 0. Therefore, the difference is 0. In this lesson, we will prove a beautiful characterization of prime numbers using floor sums. The statement is this: if for a natural number n the following equality holds, the sum of the floors n over 1 through n over n equals 2 plus the sum of the floors of n minus 1 over 1 through n minus 1 over n minus 1, then n must be a prime number. Step 1. Evaluate the simple edge terms on both sides. The floor of n over 1 is n. The floor of n over n is 1. Likewise, the floor of n minus 1 over 1 is n minus 1, and the floor of n minus 1 over n minus 1 is 1. Step 2. Substitute these values back and cancel what matches. On the left, n plus 1 appears. On the right, 2 plus n minus 1 is also n plus 1. These cancel, leaving for every k from 2 to n minus 1, the equality floor of n over k equals floor of n minus 1 over k. This is the crucial condition we will use. To build intuition, the floor function only changes when the quotient crosses an integer. If k divides n exactly, then n over k is an integer m. Reducing the numerator by 1 drops the floor down by 1 at that k. That is the only way the floors can differ. Step 3. Proof by contradiction. Suppose n is not prime, so n is composite. Then there exists a divisor p with 2 less than or equal to p less than or equal to n minus 1, such that n equals m times p for some integer m. At k equals p, compute the two floors. The floor of n over p equals m, exactly. But the floor of n minus 1 over p equals m minus 1, because n minus 1 over p equals m minus 1 over p, which lies strictly between m minus 1 and m. These two values differ, contradicting the key equality for k equals p. Therefore, our assumption was false, and n must be prime. The key takeaway is that the only k that can make the floors differ is a proper divisor of n. The equality across all k from 2 to n minus 1 can only hold when n has no such proper divisor, which means n is prime. For intuition, imagine n equals 12 and p equals 3. Then the floor of 12 over 3 equals 4, while the floor of 11 over 3 equals 3. This is exactly the one-step drop caused by subtracting 1 in the numerator when k divides n. We have completed the proof. If the given floor sum identity holds, then n is prime. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.